Thanks. I want to say thanks to everybody for great talks this morning, and I'm excited for this next discussion. Go ahead, Tobin.
I have a
Please introduce yourself and your institution.
Tobin Munsat from the University of Colorado. I have a couple of questions for the Georgia Tech crew doing dust mitigation. First question is there a maximum depth of dust pileup that your approach can handle? You know, I can imagine an extreme limiting step. You know, if you're under a meter of dust, it's not going to work. If it's a less than a monolayer of dust, it's going to work great. And so where's the medium, or where's the limit?
I think you can answer
better. Yeah, I can take this. So since we are testing it under dynamic dusting, we are not actually placing a layer that we know of which we know the depth. But what I've noticed during the experiment is that it's very rare during that kind of experimental setup to have deposition of dust that accumulates vertically. When it happens, it's still usually possible to clean up the device using the maximum voltage that it can withstand. So I will say I can think about cases with 0.5 millimeter of dust and still the device working. Oh, wow. Usually it takes some time and a few cycles to completely clean it, but it seems to be still possible, especially with the optimized design. So with the smaller electrodes, smaller interdistant, and that's very effective.
Great. And then I've got a sort of a follow-up or quasi-related question. I was thinking about spacesuits, you know, flexible, wearable, and I'm wondering if your team has ever considered, rather than printed on, circuit boards, whether using some sort of fabric or textile approaches.
So I think I can take it. Our future work will involve using different manufacturing techniques for such devices, including some other printing techniques. Because what I've been using for the CMRGO devices that are flexible is we are dispersing the nanoparticles in a chloroform solution to get the ink, and then we're putting it inside an air gun and spraying over a mask. But we're wanting to explore more techniques such as the inkjet or the screen printing that I think in which we will be able to use fabrics as the substrate instead of the plastic materials that we are currently using. So I think that would be interesting, and we are also planning on performing some work on spacesuit materials in the future too. Mm-hmm. Oh. Yeah.
Hello, Eric Duknovsky, Brown University. I also have a question for Luca and Ide. I was wondering, have you given any thought to the implications of keeping such high voltages on the surfaces of devices? You know, I'd maybe be concerned that they might damage electronics, or, I mean, I don't know how electricity arcs when there's no air, but maybe with like dust in the air, maybe the electricity would go places you don't want it to go. So yeah, what are your thoughts about that?
So thank you for the question. The first thing is, as you've probably seen, most of the research is about the dielectric coatings, and that's the first way that we have to protect any device, any instrument that is around the device. What I can think about is implication due to electromagnetic interactions. That could be an issue, for example, for instrumentation. So if you think about application to spacesuits and something that has to go directly in contact with the astronauts, then clearly the shielding procedure is very, very important. For instrumentation like solar panels, maybe you can still allow some events of micro discharge or whatever, but of course the application of decoding is fundamental for bringing these devices on a real world mission. That's the issue. Thank you.
Thank you.
Okay, we have 2 questions online. I'll do one and then we'll throw back to the room if that's okay. This is a question for Cecily. Isn't there a cross-force FDFG? Why 20 micron dust at mid-size lander? And are you going to study Phobos?
Okay, I think I'm going to try and guess what Rosemary's asking here. I'll start. I only showed some of the results that we have. So if you're asking why we showed the 20 micron dust only for the mid-size lander case, it's just the comparison case that I chose to show. Am I going to study Phobos? Yes, that's the hope and that's the plan. There's the Martian Moons exploration mission that's going to put down a lander and take a sample from the surface of Phobos, and they have a pneumatic sampler. So at the moment, we're actually looking at the Apex case, which is going to Apophis. It's the OSIRIS-REx thruster. So that's the first up on the docket. After that, hopefully we'll move on to Phobos and MMX. And isn't there a cross force? I don't, maybe we should talk more about this one on the side. We have two different approaches that we're looking at for the different forces. In our drag force that we're using, there's no gravity component that comes in. But Rosemary, you and I can chat about this one after, I think.
Hi, I'm Kayla Shang from University of Central Florida. My question is for Melissa, and I think I may have just not quite tracked all the different sizes you were saying, but I thought I heard you say that especially in the normal force simulations, your particles were 1 meter. Was that correct? And if so, can you talk more about why you chose the sizes you did?
Yeah. So for the, I call them physical validation cases, I did choose 1 meter size particles, and that was completely arbitrary. Just because the, in this case, the size of, so for specifically the normal force where they stack on top of each other, right? If I had chosen smaller particles, the difference in my final position of the particles would have just, been smaller. It would have scaled smaller. So because these are just validation tests, the actual size of the particles doesn't affect the outcome all that much. Obviously, if I were to do a rover wheel in a dust bed, I would not be using meter-sized particles. So I mainly chose that number just because we were running validation tests. Yeah.
Some light simulations are sort of scale independent, right? So you can sort of just it's 1 meter, but it's just sort of a scaled version.
Yeah,
Anyway.
yeah, that's exactly it.
Okay. Clive, I think we have one more online, and then we'll go to you. Great.
Okay, thanks for waiting. This is from John Cooper to Georgia Tech EDS. Have you investigated optical transmittance on optical surfaces, telescope mirror applications?
Yeah, thank you for the question. So at the moment, we have not considered transparency as a requirement for that we have done. We know that there is a lot of research on that with EDS made with a glass substrate and ITO electrodes. We focus more on the flexibility of the device. The whole purpose of using CMRGO is to have a flexible device. And the problem with optical transparency, I think this is the question, I got it right, is that CMRGO is not transparent, but the substrate can be, so we can have a semi-transparent EDS that could be used for some of the application requiring that kind of feature, but it's not what we have investigated up to now. Of course, it's in our plans to also focus on transparent EDS, but it's not. We haven't done that yet.
So we're planning on exploring some different materials for the conductive, such as silver nanowires. I think that would be an applicable material for our current design where we're using spray printing, so we can again disperse some silver nanowires that would be transparent onto the device surface, and with a transparent substrate and transparent coating, if we could have the conductive material as transparent but also still sustain our flexibility like the CMRG is doing, I think that would be great for the optical stuff. Thank you. Okay.
Clive Neal, University of Notre Dame. I have many questions. How much time we got? All right, I'm going to start with Cecily then and just ask. Are you modeling the launch of Starship off the lunar surface? That's the one that bothers me the most. Don't really care about Phobos because there's no humans involved, but this is the big one in terms of, are we going to lose the mission because they're launching off loose regolith?
We unfortunately cannot look at the Starship case. DSMC is a method that it can do continuum flows, which is likely where a lot of that exhaust plume for the Starship would be, but it's not the optimal way to do that. It would be very computationally expensive. So unfortunately, our method is not the right tool, and we cannot solve that mystery.
Damn. All right.
There are some other folks with that are working on
I-
Starship cases, but
Yep, I know.
they might not be as publicly accessible.
Right. And all right, so as the Georgia Tech group have had a lot of questions, I'll go to Melissa. And remember, geologist, so not a modeler. And I saw lots of wonderful, perfectly shaped spheres in your model. And how realistic is your model when you're looking at lunar regolith, which is not spherical?
That is my favorite question.
Good.
So the way that you've asked the question is not my favorite. So in the software, we are able to like stick particles together to form like agglutinates that are not perfectly spherical and that could represent, like an angular lunar particle or something like that. But to do that would be very computationally expensive.
That's the second time I've heard that. Okay, so what's the answer of how we get around this so we get accurate models for the real situation?
That is a very hard question that I don't exactly know the answer to. So I think that is why we, when I do all of this modeling, I do a model and then I get results and then I look at some experimental data that has been done with, lunar simulant, or if there is lunar data available, you do your model and then you look at the available experimental data that you have and you see like how much does this match, how accurate is it? And that's kind of like how you quantify how accurate your model is. So the like long-term plan for me would be to get these simulations working and then like recreate that in an experimental fashion in a vacuum chamber and then kind of like match my parameters so that my simulation models like what we actually see in reality. Obviously, because we have spherical particles, it's not going to be like super exact, but I can't tell you right now like what the level of that error would be.
Okay. I would start with the experiments first and do the model. That's just me. Okay.
Yeah, so
You can compare to.
Yeah, so the figure I showed on one of my slides of the wheel in the grain bed, that was from an experimental paper. So what I'm trying to do now is to get the simulation working so that I can like replicate those results first, right?
Okay.
I just didn't do those experiments.
Okay. Microphone's not on again. Keeps going on.
Battery. Even with spherical particles, there's some knobs you can turn, like the way they do the patch and the tribocharging in their model is super cool, right? And it allows you to sort of like do some of that more closely and like in lights and other DEM. The particles that are happening. And then the other thing is Lights has a paid version that the company has developed called Aspherics, in which they more easily implement multi-sphere models, which is these like sort of aggregate type things that Melissa's talking about.
Multi-sphere model.
Yeah, so they're just like little clumps of grains, but the trick with that is always like grains are conductive versus insulative, and how you get the electric charge transferred between different parts of the grain. It's a complex
So it's
problem.
non-trivial.
Correct.
Thank you.
But super exciting. Oh, Mike wants to ask a question. Or
No.
maybe plug Ryder.
Sure. You guys are popular, Luca and Ide. My question is, I think you both showed videos of the discharge device, and was wondering what the analog dust did you use? You know, was that a simulant? Was that, you know, and I would suggest getting your hands on some actual Apollo regolith samples through a request. That would be very interesting.
It's a simulant. It's LHS1. I think the same one that you use. Yeah, yeah, of course.
Did you use the regular formulation, or did you use the regular formulation, or did you use the dust formulation? So there's a dust LHS1.
We use the regular, but we sieve it ourselves to like retain the finest part of the distribution.
Thank you. Thank you very much. And I do have, sorry, I do have one comment. Just the Phobos came up in a question, and I just wanted to point out that there is a Phobos simulant that exists. It's described in a paper by Zoe Landsman. Sorry, I forgot the journal and year, but it's within the past several years. So just wanted to throw that out there.
Really quickly, we're going to do an online question. And it's from John Cooper for Jason McLean. The question is, energetic heavy ion sputtering involves dielectric explosions. Is this applicable for dust ejection?
Yeah, sure. I don't see why not. You know, I'm still surprised about how energetic these electron very low flux. So I mean, these fluxes we used were applicable to an SEP event. You know, and we were seeing all this activity. So I'm not sure what the flux of energetic heavy ions are typically, but if they're on that order, then I think it could be also another mechanism for ejection.
I have a follow-up question, Jason, since we're on you and I'm going to take chair's prerogatives. Sorry.
Sure.
So in your simulation or in your experiment, sorry, are you able to characterize like the plasma parameters at all? So are you able to characterize if there is sort of like a plasma generated or any other diagnostics of sort of what's going on? And I'm thinking about that in terms of disentangling if you're just getting like dynamic dust motion versus dielectric breakdown. You know what I mean?
Yeah, that's a great question. And actually, the early experiments focused on that. I mean, Bill Farrell and I looked at using broadband radios to try to pick up RF discharge signals, any EM signals. It was extremely difficult to pick that signal out, even going through many kinds of different lab equipment and spectrum analyzers and such. So we did run a mass spectrum to see if anything we could pick up, you know, gas being expelled during these ejecta, and that was also very inconclusive. It did look like oxygen increased, but with this setup that we had at the time, it was unclear if that was due to the explosions or not. So yeah, it's really hard to do any sort of detection that we found externally. We tried everything I could think of and our team could think of, and in fact, coming to this laser fan was really like, oh wow, there is a lot of stuff happening right under our noses. So we didn't know. I mean, of course, you can get any material to break down, but not, you know, at these low fluxes. It was I think that was the surprising part. I hope that answered your question.
You can't see me nodding, but yeah, thanks.
Hi, Alex Donner at the University of Colorado Boulder. Questions for Melissa.
part of your coding challenge seems to be that you're switching from some perfectly spherical grain to a CAD file that is a whole bunch of vertices that represent sphere. Since you're using a CAD file already, is there a reason you can't use a non-spherical CAD file to sort of get approximations for non-spherical grains?
I don't like that you asked that because I was just thinking about it. Yes, there's a very good reason why I don't do that. So for comparison, the last two slides that I showed had the 3 grains like stacking on top of each other. The slide where it was like just the DEM grains, that simulation runs in like 40 seconds, right? And then the next one that has the 2 DEM grains and then the mesh file with all of the facets, that takes like 20 minutes. So if I were to have like thousands of little CAD files with different, vertices to make them all angular, it would take, forever to run. And I think at that point, you would almost be better off writing like a new simulation software to be able to handle that better, because Lights really wasn't built to like handle moving mesh files. Obviously, I made it do that. So I think at that point, you'd be better off to just like rethink your modeling software to be able to make something like that. Does that make sense?
Okay, then I have a follow-up question. In that case, then why use a CAD model for a sphere at all? Because I could trivially define non-spherical shapes with just as many or fewer vertices than your sphere, and then I wouldn't understand your present argument for why you're pursuing this.
Clive is going to shoo me off of the stage. So if I wanted to make a wheel made out of grains stuck together, right? Because that's the alternative. You would need to stick a lot of grains together to, have it look like a wheel and have a flat surface like a wheel. And again, that becomes very computationally expensive to run in a simulation. Did I misunderstand your question?
No, I think maybe I misunderstood earlier. So you're pursuing CAD just for the wheel?
Yes, it's only the wheel.
And all dust will be perfect.
Yes.
Got it. Okay.
Yeah. Okay.
Got a follow up to that as well. And this, so for Melissa and also for any other modeler in the room can chime in. I'm not a modeler, but being trained in mineralogy, where I would start with the modal mineralogy of what you're looking at. So for LHS1, you've got anorthite plagioclase, which we know the crystal system, we know the unit cell, and does anybody model using those types of parameters? I'm sure it's more time intensive, but that's where I would start as a mineralogist.
Well, I mean, you can use realistic material parameters in these simulations, but the way Lights and most DEM software handle like a physical object is that it's a sphere or like a wall. You don't enter like crystal structure and things like that. But you can use, and Cecily can chime in if she wants to, but you can use realistic physical properties because you put in things like Young's modulus and other physical properties in these modules. So you use those to generate the spherical behavior, the behavior of the spherical particles.
So this is Clive again, geologist, not a modeler. So what you're saying is the shape is irrelevant to the model.
No, I'm saying that the model, most DEM simulations, including Lights, which is what a lot of folks use, but even other simulations done at Maryland and other folks typically use spherical particles. There are some simulations, Derek Richardson's group at Maryland and some other groups have been using PKD Grav and some other simulations that have like faceted particles that are differently shaped.
Yeah, so I come back to the model versus reality. How applicable is the model to reality?
Yeah,
that's my issue.
I mean, I'm also not a modeler, but that's
Can
why
I chime in for a second?
Yeah, please do. Thank you.
Yeah, well, I mean, I'm just actually going to continue saying what Addie is saying a little bit. First, I know this is it is a big topic in modeling, and there's been a lot of work that has looked at how you could, how realistic is this? And there's ways around other than just doing faceted grain shapes. You could do like aggregates. So actually Derek Richardson's group, and I think maybe Lights could do this too, is you could do elongated particles, you could stick particles together in different ways. So they're still kind of spherical, but they're also getting different grooves and shapes. And there are parameters in the DEM codes that let you tune for things like angle of friction. So, generally when you have more angular particles, that's going to show up in your angle of repose or your internal friction angle. And there are simulation parameters that let you adjust this. So like what Melissa was saying before is generally what we do is we have some experimental case that we use to calibrate the simulation parameters. And that experimental case isn't necessarily with spherical grains. And then use several experimental cases to match the behavior of the experimental ones, and then use the simulations to do things like take away gravity or go to cases that you can't do experimentally. So and then one more note, there's a group in California that has this thing called level set DEM, and they actually do a scanning, like they scan grain shapes and they replicate those with these meshed slices building up. It's called like a level set. You have to picture like stacking meshes on top of each other, whatever. It's like the most highly accurate simulations you can get. Again, at the cost of computational time, there are ways to do it. And so I think while it's not perfect, it is like, the computational community has been working on this for decades, matching it. So there are ways to go about it. Anytime you're starting with something new, like Melissa, of adding in a new feature, you really have to start with the spheres to make sure that like your contact models, your contact forces, and everything is predictable and matching some analytic model. And then from there, you could, go crazy. But lots of methods. If you're interested in like finding the right DEM software for you, I could help you out. You could send me a message, and we could chat about it. I have a strong catalog of everything out there at this point.
Yeah, introduce yourself.
This is a question for Jason. Looks like he may have disappeared.
Introduce yourself, Tom.
Excuse me, Tom Orlando from Georgia Tech. Hi, Jason. Good to see you.
Hey, yeah.
I missed this. You were clear that your electron fluxes were low, but do you have an idea of what the actual fluxes at the interface do to the secondary electrons that are generated? Because those are the ones that are going to be sort of mostly about trapping in any kind of discharge. So do you have any idea of what the role of the secondary is?
No, I don't. And, that's part of the modeling effort that Tim Stubbs is leading on our team to see electrically what we have happening. Especially once you get to the 100 keV electrons. I mean, these are relativistic and going through multiple grains potentially, and how that interacts coming out or through, and the secondaries involved in that. We need to do a little bit more work modeling that behavior. So
it's on your screen. It's clearly on your screen. That's what we're saying.
Yeah, definitely. There does appear to be some different physics occurring here than just this dust hopping, though. But right now it's still, we can't 100% rule out that this isn't just charge building up in between the pores, and causing these expulsions or these ejecta.
Thank you.
Yeah.
Mike has one more question. Yeah, we have until in theory we could keep going until 11, but we'll probably do one more question and then wrap it up.
Mike Luke's Florida Space Institute. So, Jason, more of a comment than a question. A secondary application for what you showed may be an effective method to produce agglutinated simulants. Comment on that.
Yeah, the SEM, of course, it's really hard to look at a bed of grains and to see discharge effects. But, there's a lot of evidence that grains were ejected and there's agglutinates being formed and particles being welded on the grain surface. Our SEM expert who's been looking at this, Morgan McLeod, has a lot of images of the before and after effects. But yeah, seeing these agglutinates was really, really cool find. And I agree. I mean, these are very interesting materials.
I thought it was cool too, and thank you for your answer.
Yeah, sure.
Great. Do we have any more very, very quick questions? Great. If you do have questions, please follow up with each other and with our speakers. And can we give our speakers another round of applause?